All right, my dearest chemistry friends, welcome back to Quantum Principles, your favorite course. We had a little break on Monday, so there was no lecture. And so what I'll try to do is to make the connection with the stuff that we talked about last week, because we're moving at a pretty good pace in this course right now. So we are going to be finished with covering the main material before the end of the quarter. So we'll have 2 lectures that are kind of like undetermined. So we have that time to really talk about the material that we already covered and to basically dot the I's and reflect back on some of the things that we have talked about. So just to make sure we use those 2 lectures to really, consolidate all the stuff that we have been talking about. Make sure everybody understands all the principles. So today I am going to talk again about, putting electrons in orbitals. This is basically the Aufbau principle. I think most of you are familiar with that principle. But maybe you don't really exactly know where the rules come from, the Aufbau principle rules. And so today we're going to look at that once again. So this all relates to the wave functions that we have found, the orbital wave functions that we have found for the hydrogen atom. That's where it all started. Okay, so the first line you see here is that general solution for the wave function of an electron that sits in the hydrogen atom. Okay, so the general way of writing that, of course, is capital Psi, and then the quantum numbers NL and ML, and then the 2 functions that really define the shape of that orbital, which is the radial part, which depends on N and L, and then the spherical harmonics, which basically determines the angular part, which also has the quantum numbers L and ML. So the energies of these wave functions are shown here. This by now is pretty clear, I hope. We have the 1s, the 2s, the 2p, 3s, 3p, 3d, and so forth. Those are the energies associated with the wave functions that follow directly from the solution of the Schrödinger equation. Okay, and so the beautiful thing about this solution is that it's exact. We did not make any stringent approximations. And this is an exact solution that corresponds really precisely with the observations that people have made. So again, one of the triumphs of quantum mechanics, it fully explains the behavior of the electron when it's part of a hydrogen atom. So the energies are degenerate, as you can see. And we have already touched on the fact that if you are now going to an atomic system with multiple electrons, that this degeneracy for each of the states in a given level defined by n, the principal quantum number. So degeneracy means here, for instance, 3s, 3p, and 3d are all at the same level. They all have the same energy, so they are degenerate relative to one another. But that degeneracy is going to be lifted as soon as you have more than 1 electron. So for any other atom but the hydrogen atom, you will have an interaction between the electrons, right? Because if there's more than 1 electron, there will be an electron-electron interaction. We wrote that in terms of this J, the integral that basically says how the electrons in the system interact through this Coulombic potential, right? So this is just a Coulombic potential right here. That is the Coulombic operator of 2 electrons repelling one another. And then we basically have the the individual wave functions of the 2 particles. They're sandwiching, so the total state is sandwiching this operator, and that gives us kind of an impression of the Coulomb electron-electron interaction, right? And because of this electron-electron interaction, things look a little different in the other atoms but hydrogen. The energy states of the wave functions are now kind of at different locations, okay? And that is because, for instance, the 2s, the shape of the 2s is such that the electron-electron interaction can be somewhat minimized if the electron is very close to the nucleus, thus benefits from an extra attractive force, which lowers the overall energy of that state. Okay, so that is basically seen as well in the level 3, 3s, 3p, 3d. This degeneracy is lifted because of this penetration effect. Basically, the penetration effect is related directly to the Coulomb interaction. Okay, so that is something we have already touched on. Now, what we have not really fully touched on yet, and this is something we started to talk about last Friday, is if you have multiple electrons that have to be filled out, you have to put them in some of these orbitals, then the question is, where do they go? So how can I achieve the lowest possible energy state, not just of one electron, but of 2, 3, or 4 electrons? Where do they go? You have to put them in certain states in such a way that their interactions are going to be minimized, and the overall energy of the system is going to be minimized. So that depends not just on where the energies of these orbital states are. So it's not just defined by the orbital state energies, which is given in this diagram, but it's also defined by how electrons accommodate or occupy these states, because that defines how electrons will interact with one another, right? So that is that's an extra layer of complexity on top of knowing where those energetic states are. The way they accommodate or occupy these states will have an effect on the overall energy of the system. Electrons can be in state where they interact very strongly, or they can be in states where they basically don't really see one another, and that's a very different state for the system to be in. Okay, so today we're going to talk about that once again, starting with what we talked about on Friday. We concluded that there is something that's called the Pauli's principle. And the Pauli principle, the word on the street is always, okay, you can only put 2 electrons in a single orbital, but that's not really what Pauli's principle states right off the cuff. It says that a fermion wave function, which is what an electron wave function is, must be antisymmetric. Remember that statement? Antisymmetry means that if you change the occupation of the particles, so you swap the labels of the wave function, particle 1 becomes particle 2, that is particle exchange, that's what it's called. So upon particle exchange, the wave function must change its sign. And if that is the case, then the wave function is antisymmetric. Okay, so for a fermion, the total wave function must be antisymmetric. It's a very stringent restriction. So for the ground state of helium, this is what we've done on Friday, we found the following. Okay, let's look at this one more time because it's kind of important. So we have here the situation where we have 2 particles, 2 electrons, electron 1 and electron 2. Now, both of these electrons are going to be in the 1s orbital state. Okay, so I'm going to try to put them in the 1s, both of them. Okay, so particle 1 at location R1 and particle 2 at location R2, they are both in the orbital state 1s. Now, what is their spin state then? And on Friday we concluded, well, if that is the case, the spin state, indicated by this sigma minus, must be antisymmetric. That's what this negative sign stands for. It must be antisymmetric. Why? Because that's the only way in which we can make this total wave function antisymmetric. That also means if the spin state, sigma minus, is antisymmetric, then the orbital state, which is this part, must be symmetric, right? And that is indeed the case, because it doesn't matter if you swap the labels of R1 and R2, because they're both in the same state. So nothing is changing. Since they're both in the same state, if you swap the labels, the situation hasn't changed. And therefore, this part, the orbital state of the wave function, is symmetric. The spin state is antisymmetric, and that is the part that makes the overall wave function, that's what this guy is, antisymmetric as well. Okay, so this is the ground state of helium. It's antisymmetric, so it complies with Pauli. And this is the way we can write it if you do a good job at basically writing out the sigma minus. So the definition of sigma minus is given right here: alpha 1, beta 1, minus beta 1, alpha 2, right? Where alpha and beta are the spin states in which the electron can sit, spin up or spin down. Okay, so this is really what we concluded on Friday. Nothing has changed yet. This is the same thing. The new thing is that I'm going to write this in a slightly different way, namely in this way, okay? So what is this all about? Well, this is called a determinant, and I'm sure you are familiar with what a determinant is. If you're not, then this is the definition of a determinant. So the determinant, the thing between these two modulus signs, is whatever this argument is, A times D minus B times C. Okay, so that's really what the determinant is. Just a shorthand writing of this operation, AD minus BC. Okay, so the line above here, this line, this whole line here, I can summarize with this determinant. So if I multiply this, this is A, and this is D, so this term times this term, that's A times D, minus this term times this term, that is B times C, is going to be exactly the line above it. Okay, so it's just a shorthand writing of the line above it. Nothing has changed. Okay, now why do I do this? It turns out, if I write things in this way, I have first of all, a more compact way of writing things. Okay, because in some kind of situations, the line above it can become very large and it becomes very hard to understand what's going on. This way of writing it sometimes can be very useful, compact, and if we stick to this rule of determinant, the determinant always makes sure that the resulting wave function is antisymmetric. So let's look at that a little bit more carefully. So what we're going to do is we're going to take these arguments here, okay, and we're going to kind of give them a name. We're going to give them a name. We call them spin orbitals. Spin orbital. Spin orbital is basically a single electron state, where there is an orbital state. So this psi A is the orbital state, and there's a spin state, but just for one particle, not for two particles. Just for particle one, in this case, the spin orbital says particle one sits in orbital named A, and it has a spin state alpha. Okay, so whatever A is, could be 1s, 2s, 3s, 2p, whatever the orbital state is, and then alpha, of course, means spin up. Okay, the spin up state. So this is basically the spin orbital of particle one. But of course, this particle can also be in a beta state. Okay, so it could be in the same orbital or another orbital, whatever A is, with a beta state for the spin state. Okay, so this is just, a different way of writing the situation for one particle. So then we can write generally the following. If you have a two-particle system, that means that the overall wave function is now a function of particle one and particle two, can be, in general, written as follows. 1 over square root of 2, which is the normalization constant here. And then this determinant, and the way we do this is that the first line, or the first row, basically lists all the possible spin orbital states of particle one. Okay, so this is really the row for particle one. This is the row for particle two. Okay, so we go row by row, and each row is the possible states in which particle one can sit, written in this kind of so-called spin orbital way of writing things. So what are the possible states in this particular case for ground state of helium that particle one can be in? Well, particle one can only be in the ground state. So this A is going to be 1s, and this A is also going to be 1s, because we demand that particle one, electron one, sits in the 1s state. That's what we want. And then I say, well, it has two possibilities to sit in this state. Namely, it can sit in the alpha spin state, or it can sit in the beta spin state. We don't know if particle one is spin up or spin down. We don't know that, right? So we have to say the two possibilities for electron number one is that it sits in 1s, and it can either be spin up or spin down. Those are the two possibilities. And then we're done with the possibilities. Then for particle two, same story. Particle two also sits in state 1s, which is what A is in this case, and then alpha or beta. Okay, so the same thing for particle two. Particle two can also be spin up or spin down. We don't know what the state is of particle two. either one is equally likely. And so we give basically those possibilities in this determinant. All right, so basically if we do that, then we get the same function back that we just showed on the last slide. Now this thing, this way of writing has a name, and it's called the Slater determinant. Maybe you have heard of Slater determinants in a different course, right? And this is a useful technique for chemists and anybody else who is interested in writing the total wave function of a multi-electron system. Why is it so useful? Because it doesn't only apply to two particles, although the two-particle case is the most clear to explain and understand, but you can expand it to a multi-electron system as well. So that is given over here, where I have on the first row, once again, all possible states, spin orbital states in which particle 1 can sit, all possible spin orbital states in which particle 2 can sit, all the way to particle number n. Okay, so you construct it in exactly the same way, and then do the determinant 1 over n, and then this exclamation mark here, factorial, and that will give you the normalized anti-symmetric wave function. So the beauty of this Slater determinant is that if you write it this way, then the resulting wave function is always going to be anti-symmetric. Okay, if it is not anti-symmetric, then the Slater determinant will return the number 0, meaning there is no wave function. So that's why this is very useful. If you don't believe that, let's put it into practice. Okay, so we'll do that in 2 seconds, but first I have to go through the following just to kind of make sure that everybody is aligned with the discussion here. Because all of this, of course, pertains to understanding how electrons are organized in the orbital states that we have for each of the elements, right? So we already know that the properties of the hydrogenic wave functions are key. Okay, so that basically gives us the template, the blueprint of how the orbital states are organized. Then we have the Coulombic electron-electron interaction, which lifts the generacies. Okay, that's ingredient number 2. These two statements, once again, these two statements define the energies of the orbital states. Okay, so we haven't put any electrons in our system yet. So there's no particular spin-spin interaction or spin-orbit coupling or whatever. This is just where the orbital states are in energy space. And then we have the exchange interaction, okay, which basically means how do electrons accommodate the different states. And we have to abide by Pauli's principle. Pauli's principle is also known as the exchange interaction. So Pauli's principle, it doesn't define the energies of the orbital states. It basically gives us a guideline in how the electrons will occupy certain states and which arrangement of electrons in either one of these states is going to give us an overall state that has the lowest possible energy, right? That is what Pauli's principle is going to give us. So these 3 ingredients will basically determine the ordering of the the elements in the periodic table. So, and we'll see at the end of the lecture how that comes into play. Okay, so first, we're not out of the woods yet. So what I'm going to show you is, first of all, how this Slater determinant can be very useful. Okay, and then later, how we can use it to prove Hund's rule. Okay, Hund's rule you have heard of. Hund's rule basically says that the lowest possible energy that you can have in a multi-electron system is if you maximize the overall of unpaired spins. Okay, so and that is an interesting rule, but the question is where does it come from? It seems pretty arbitrary, and you can see from this lecture, hopefully at the end, that there is a reason why that rule actually applies. Okay, so let's consider now 2 electrons in the 2s orbital. So this is not necessarily helium. This could be a different orbital, different element. I'm going to ask myself the question, I have the 2s orbital, and I'm going to put 2 electrons in there. Okay, so The first possible way in which I can do that, if I have two electrons and I want to stuff them both in the 2s orbital, is if the two electrons have the same spin state. Let's say alpha or beta, doesn't matter, but they are the same. Okay, so I'll choose alpha for this, for the sake of the argument, because the result for beta is going to be exactly the same. So what do I have for my Slater determinant if I do that? Well, again, the first row lists all the possibilities for particle number 1. Okay, so again, let's go through it. The first possibility for particle number 1, it sits in a 2s, so that must be the same for both particles, and it can be in state number alpha, spin up. Okay, but I already said that I required that both particles will have the same spin. Okay, so I require for the second option the same thing, still alpha. I don't want the spin to change. I say the spin must be alpha. I'm going to fix the spin state of particle 1 and also the spin state of particle 2. So this looks a little silly. It looks like the two possibilities are the same, and that is just because I demanded that the spin must be spin up. Okay, so the only possibility is the spin up. I must have a second possibility, but this one is the same. So that's why I'm repeating the same possible spin orbital for particle 1. So particle 1 can accommodate 2s only in one way, that's a spin up. The second possibility is also spin up because there's only one possibility. I have to put two possibilities for each electron, at least that's the minimum. And so this is why I have to list this possibility twice. The same for particle 2. So the resulting Slater determinant, which is necessarily for a particle system of 2, 1, 2, must be a 2 by 2 determinant. So this is the only way I can make this 2 by 2 determinant, which basically means listing the possibility twice. If I do this, what I find is the following. After multiplying out the determinant, I can see that I have the orbital state 2s for particle 1, orbital state for particle 2, which is also 2s. And then I have this spin state right here. Okay, so again, as always, what you will get is you get an orbital state and you get a spin state. But this is an interesting spin state. It's not an antisymmetric spin state because it says alpha 1, alpha 2, alpha 2, alpha 1. So I can easily swap this. It doesn't change anything. Doesn't matter. The order of multiplication doesn't matter. Basically meaning alpha 1, alpha 2 minus alpha 1, alpha 2 equals 0. Okay, so what I'm getting is that this wave function is not allowed according to the Slater determinant, which means there's no way you can construct an antisymmetric wave function if you try to put two parallel spins into one orbital. Okay, so this is yet another way of saying Pauli's principle means that you cannot put two parallel spins in a single orbital. We already know that, but this is another proof of the same thing. The R1 and the R2 means location of particle 1, location of particle 2. Okay, so I can simply write 1 and 2. Okay, I write R1 and R2 because the orbital state is giving me information about location of particle 1. That's why it says R1. I can easily say particle 1 simply sits in orbital state 2s. Particle 2 also sits in orbital state 2s. All right. Okay, so now the second case. We know this second case must give us a good answer, okay? Because we know that Pauli's principle says if you put two electrons in a single state, then the spins must be anti-parallel. So let's do the same exercise once again. So both are now in 2s, okay? The two possibilities in this 2 by 2 determinant for particle 1 are these two possibilities. So now the second possibility is not the same. The second possibility is different. It's beta. Okay, and the same for particle number 2. So this is the 2 by 2 determinant that I can write for this case, case number 2, where the two electrons have different spins, but they're still accommodating the same orbital, in this case, orbital 2s. Okay, so this, if you multiply this one out, you can see again, I have a orbital state, and the orbital state is the same as the one before, but the spin state here is not the same as the one above. because now I have alpha 1, beta 2, alpha 2, beta 1. These two terms are not the same. If I swap the order of beta 1 and alpha 2, so beta 1 goes in front and alpha 2 goes second, that term is not the same as the first term here, the first multiplier, okay? And therefore, this subtraction is not going to give me 0 because these two terms are different. And therefore, this is not equal to 0, right? So this is a valid solution. It is not equal to 0. This is a valid finite wave function. It has amplitude, it's not 0. And that means that this is a valid solution of my problem. It's an anti-symmetric wave function where both electrons are in state 2s, orbital state 2s. They must have an anti-symmetric spin state, as we have already determined. Okay, so spins of 2 electrons in an s orbital must be paired. Pretty clear, pretty evident, but again, done in a slightly different way through Slater determinants to prove that fact. This slide shows that if you are trying to force a situation that is not allowed, the Slater determinant is going to give you the answer 0. If you are constructing a situation that is allowed according to Pauli, the Slater determinant is going to be finite. Okay, it's not 0. So this is what this particular slide is trying to illustrate. Okay, so this is the scenario where I put 2 electrons in a 2s orbital. Now I'm going to do the same thing, but in a 2p orbital. Okay, why is that going to be different? Well, it is different because there are 3 possibilities for a 2p orbital, right? Every p orbital comes in 3 flavors. ML is -1, 0, and 1. Those are the 3 different possibilities. And so I can put the electron now in different orbital states. Now the end result is the same. I need an antisymmetric wave function, but you will see that the solution is going to be slightly different. So in the first case, I'm going to do the following. I'm going to have the 2 electrons that will now occupy a single 2p orbital. So let me just draw that to make it clear. You have, of course, 3 orbital states for any p orbital. In this case, a 2p orbital. There's 3 flavors, 3 different states, because ML can have 3 different values, right? So what I'm going to do now is I'm going to say, well, the first electron goes in one particular orbital state, this one, the first one, and the second one is going to go in the first one too. Okay, so I'm not going to put the second one somewhere else. I'm going to put it in the first, meeting up with the first electron. And if I do that, I already know that these 2 electrons must be paired. So they must have different spin states. So I'm going to construct the Slater determinant for that case. And this is how I'm going to do it. Listing the possibilities for particle number 1, listing the possibilities for particle number 2. It must be in this orbital state, okay? So that doesn't change, but it can do so either in the alpha or in the beta way for particle 1, and exactly the same story for particle 2. It must be in the first p state, okay? So 2p1, let's say I call this 1, I call this 2, I call this 3. So 2p1, those are the states. I'm going to put both in the first one, that is the p1 state. And so both electron number 1 and electron number 2 must be in that state. So this is the Slater determinant. Let's do the multiplication and see what we get. Here it is. After the multiplication, I'm going to collect the size, and I'm going to collect all the spin states to write it out in, again, an orbital state here times a spin state. Okay, and the result probably looks pretty common now. I have here an orbital state where the orbitals are the same, 2p1, and just the particle numbers are different. Okay, so I don't write the R1 and R2, but this is the same as R1 and R2. It's the same thing. I'm just saying this electron accommodates this orbital state. I can swap the order of these guys. It doesn't change the orbital state because the orbital state is the same for each. So there's no change there. That means this part I can call symmetric. Okay, this is a symmetric orbital state. Now, the spin state, we recognize now, this is actually sigma minus 1, 2. That is an antisymmetric spin state. Okay, so the overall wave function is antisymmetric, and therefore it is not equal to 0. This will not subtract to 0, and therefore this is not equal to 0, and therefore it is a valid solution. Okay. Okay, we already knew that. That's nothing surprising. But the second part is a little different. Okay, so now I'm going to say I have unpaired spins. Now I already know if I'm going to do that, I have to put the 2 electrons in different states. So if I put the first one here, and I demand that the 2 electrons will have the same spin state, then the second electron must go in either one of the other p orbitals. Let's say the second one. Doesn't matter which one, but it must be in a different one. 1, 2, 3 states, orbital states for the p. The first electron goes into the first state. The second electron must go into a different state, either 2 or 3. Right? So that's what I'm going to investigate now. I already know that if I put this guy and I put it in the same one, then I'm going to get a Slater determinant that's going to give me 0. I don't want that, so I want to put it into another orbital state. And this is what the Slater determinant looks like in that case. So particle number 1 must be in 2p1, okay, in the alpha state. So I want both to be spin up, okay. Particle number 2 must also be, could be in the first one, also with spin up, or it could be in the second one, also with spin up. Right? So basically, the possibilities for each particle are the following. Particle 1 can be in state 1 or could be in state 2. I don't know which one is which. I don't specify that the first arrow is specifically particle 1. This could be particle 2. This could be particle 1. Okay, so that basically means the possibility of each electron is either accommodating state 1 or state 2, but in both cases, the alpha spin state must be selected. So that is basically the possibilities for particle number 1, for electron number 1. It can be either in orbital state p1 or p2, but the alpha must be alpha. The same for particle 2. So this is what the Slater determinant looks like in the case of unpaired spins of 2 electrons that now are in different p orbital states. And the result is this. If I multiply this out and again collect terms for the spin states and the orbital states, you see something very, very interesting. Hopefully you can see this as well. Okay, because now it looks different. I get now alpha 1, alpha 2, and I'm going to write it first to kind of draw your attention to the fact that this looks very similar to the first term in the line above it here. Okay, it looks very similar to the orbital states. A symmetric orbital state. This is a symmetric spin state because the order doesn't matter here because these states are the same, both alphas. So this one here, the first term here is a symmetric spin state. Alpha 1, alpha 2. Now, if the overall wave function has to be antisymmetric, but the spin state is symmetric, the spin state is not going to give me the antisymmetry. So the antisymmetry must now come from the orbital state. And that's exactly what you see here in the second term. The second term is an orbital state written in a funny way, but it is definitely antisymmetric because this, first of all, is not subtracting out, doesn't give me 0. And if you swap the labels for this orbital state, you get a negative sign, okay? You get the same state with a negative sign, and that means it is antisymmetric. Okay, so the orbital state here is antisymmetric, while the spin state is symmetric. All right, so basically the roles of what the spin state does and what the orbital state does has been swapped. Okay, the roles have been swapped here in these two cases. So let me just go back to case number 1. The spin state is the antisymmetric spin state, sigma minus. Okay, it has basically capital S equals 0. This is from Friday's lecture. The antisymmetric spin state has capital S equals 0. That means the multiplicity, spin multiplicity, is 1. In other words, this is a singlet state, a spin singlet state. Okay, so I have a spin singlet state, and I have a symmetric orbital state. Okay, now the second case. Second case, I have a triplet spin state. Why? Because both of my electrons have the same directionality of spin. both in alpha, both have half. Half plus half equals 1. So the capital S is 1. 2s plus 1 equals 3. So the multiplicity is 3. There's 3 possible projections of this spin state. Okay, so this is a triplet state. So the spin state is triplet, and that means that the orbital state is antisymmetric. So for a triplet spin state, I have an antisymmetric orbital state. For a singlet spin state, I have a symmetric orbital state. All right, so let's look at the following cases: the symmetric spin state here and the antisymmetric spin state in case number 2. It's different. And now I'm going to ask the question, okay, fine, these are 2 possibilities, case 1 and case 2. Which one of these possibilities gives me the lowest energy? Which one is the most favorable? Okay, now it turns out the orbital states here are going to give us the answer. It turns out that the antisymmetric orbital state leads to a situation where electron repulsion is going to be minimized. This is a theorem that is related to the formation of a so-called Fermi hole. I will not go into the details. I'll be happy to talk about it if people are interested. But the bottom line is this: an antisymmetric orbital wave function gives rise to reduced electron-electron repulsion, and therefore gives rise to a lower energy state. Okay, a lower overall energy of the state in which my 2 electrons combined sit. Okay, so if I have to choose between a symmetric orbital state and an antisymmetric orbital state, then the antisymmetric orbital state will give me the lower energy. In other words, if you have 2 possibilities to put the electrons in these degenerate orbital states, then the triplet state way of doing it is going to give me the lower energy, and the singlet state is going to give me a slightly higher energy. All right, so antisymmetric orbital wave functions have lower electron-electron repulsion and thus lower energy, aka the triplet spin states associated with this antisymmetric orbital wave function is going to give me the lowest possible energy. All right, so I'm going to now summarize that fact, okay, in the following way. I have a wave function which always has 2 parts, an orbital state and a spin state. If I have 2 particles, I say 1, 2, 1, 2. So this overall orbital state is the orbital state of 2 particles, and the spin state is the spin state of 2 particles. The spin state can be symmetric, of course, and this is what we talked about on Friday. There were 3 possibilities. There were 3 possible ways of organizing the spins that had the property of being a symmetric spin state. The first one was sigma 0 plus, sigma 1 plus, and sigma minus 1 plus. Okay, so the first case can be considered, let me just go like here. This alpha means both are up, both are spin down, and this is a funny combination, okay? But this is also a symmetric spin state, meaning that the spin state doesn't change its sign if you change the labels of these particles. All of these states are symmetric spin states. If your spin state is symmetric, then your, let me go to the orbital state first. Then the orbital state must be antisymmetric. Okay, this is what we just concluded. Because the overall wave function, given over here, must be antisymmetric upon exchange of the particles. So if the spin state is symmetric, it's not going to give you antisymmetry. That means the orbital state must do it. And that's given over here by this orbital state. Now, the other possibility for the spin state, of course, is antisymmetric, right? That means it will take care of the antisymmetry of the overall wave function. And if that's the case, that means that the orbital state must be symmetric. Now, in analogy with the spin states that are symmetric, I have 3 possible ways in which I can construct a symmetric orbital state. And it looks exactly the same as a spin state, with just the spin states replaced by orbital states. Okay, so psi A, psi B, particle sits either in state A or state B, and then the plus combination of the reverse. Now, this is another possibility. Both particles sit in the same state, state A, or in the other state, state B. So these are the 3 possibilities that I have if I have two independent orbital states. If you have only one orbital state, let's say A, and both must go into that state, then I only have one symmetric solution, of course. But if you have two different orbital states in which the particle can sit, then there's three possibilities in total. All right, so the first kind of scenario here is spin state symmetric, therefore orbital state must be antisymmetric. Okay? And that means all triplet states have antisymmetric orbital states. Hopefully that's clear. If you have a spin state that is a triplet state, then the orbital state must be antisymmetric, which means that's typically the lower energy solution. So triplet states are typically the lowest energy state that the two-electron system can have. Vice versa, all singlet states have symmetric orbital states. Okay, so the antisymmetric spin state is a singlet state. That means that the orbital state must be symmetric. Okay, so and we have seen examples of either one of these. All right, so then back to Hund's rule. This is the last slide. Hund's rule typically says the following. The term with the maximum multiplicity lies lowest in energy. That is what it says. It says the term with maximum multiplicity lies lowest in energy. And the reason for this is not exactly why most people think it is, because you may think, well, I'm going to put these spins in different orbitals so they don't interfere exactly with one another. That's not exactly the reason why, because you also have to take care of the orbital state. And it turns out the orbital states define, to a large extent, why the energy is lower if you put the electrons in different orbital states. Okay, in the case of two electrons, this means that the triplet state lies lower in energy than the singlet state. One of the reasons for that is that the antisymmetric orbital state associated with the triplet state is lower in energy than the symmetric orbital state. That's what we just discussed. Now, with this extra rule, we can now use the Aufbau principle, of course, and find the ground state of the first couple of elements, the lowest elements in the periodic table. So let's look at a couple. Of course, hydrogen, the first electron goes in the 1s, and for helium, the second electron goes also in the 1s. Okay. Then for lithium, I'm done with the 1s, so the 2s gets the third electron, and beryllium has its fourth electron also in the 2s. They must be paired. That's the lowest possible energy in which you can arrange these 4 electrons. Now, boron has 1 extra electron, so it must go in the 2p. That's the first available state in which the electron can sit. But now, of course, for carbon, I have 2 possibilities. Possibility 1 is pairing up with the first, and possibility 2 is it must go into a different orbital state. And that is what we just discussed. It goes into a different orbital state because it will generate a triplet state. And triplet states have antisymmetric orbital states, which is lower in energy than a symmetric orbital state. And that's why this configuration is lower in energy than the configuration where they pair up. Okay, same story holds for nitrogen. 1 more electron must go into the last available orbital. Okay, this maximizes spin multiplicity. Okay, and it also lowers the orbital state wave function again. Oops, oxygen has no option, must pair up. Same for fluorine. The 5th electron in the p must pair up with an existing electron. And then finally, neon, really the last electron has no option but to pair. Okay, so the interesting part, of course, is for carbon and nitrogen, where you have this Hund's rule play out in full effect, illustrating this principle we just talked about. It has everything to do with the exchange interaction, which is defined by Pauli, and the fact that you have to realize that there is something called spin multiplicity and symmetry of the orbital state, which defines which of the possible arrangements is going to give me the lowest energy. All right, hopefully that was clear. It can be somewhat confusing when you hear it for the first time. But please look over the notes carefully, and if you have any questions at any time, let me know.
Can you go over the jump from carbon to nitrogen, the thing you mentioned earlier? The animation?
Yeah. Carbon is right here. Nitrogen has one more electron and must go into the last available orbital. Did you have a question about this?
Oh, no, I think I got it. Thank you.
Okay. Okay, folks. Feel free to ask more questions. I'm going to stop the recording, and hopefully we'll see you back on Friday.